Right, I click the wrong button. So the video stopped. Okay, let's see the second one. Let's graph first. So first one, let's graph with a green color. So this is a rational function. So we're going to think about a reference graph. Remember the reference graph is is 1 over x, right? If it's 1 over x, we have this piece in the first quadrant, or this piece in the third quadrant. But x plus 2, we see a vertical asymptotes at x equals -2. So let's see this is -2. So let's draw vertical asymptotes here first. Then our graph is here. So this is the first piece in the first quadrant. Then we have another piece in the third quadrant. So the end behavior on the left-hand side says, when x approaches -infinity, the function value approaches to 0. This arrow says, when x approaches -2 from the left, the function value approaches -infinity. On this side, this one is saying, when x approaches -2 from the right, which means a number a little bit bigger than -2, the function value approaches to positive infinity. When x value approaches to positive infinity, the function value approaches to 0. So that's the end behavior. So we have those two pieces for the first one. For the second one, let me change my color to be blue. Let's draw the second one. The second one, when I draw, is very similar to the first one, but with an open circle. Why? Because this one can be simplified. The denominator is a difference of 2 squares. It can be factored as x minus 2 times x plus 2. Right? Then x minus 2 is a numerator in the numerator, is a factor in the numerator. X minus 2 is a factor in the denominator. So x minus 2 divides x minus 2 becomes 1. So we're left with 1 over x plus 2, which equals to f of x. So after simplification, it's the same as f of x. But the domain are different. So domain for the first one is x not equal to -2. Not equal to. Let me slash through the equal sign. Domain of G is x not equal to -2 and 2. Right? So -2 and 2. So that differ, the domain are differ by this number 2 here. 2 is in the domain of F, but 2 is not in the domain of G. So let's see if 2 is here. Then the rest of the graph are very similar. So let's see, this is -2. Okay. We have vertical asymptotes here. Well, we were supposed to have a vertical asymptote at 2, but because this is simplification, so it becomes an open circle. So when x equals 2, we get a quarter. So x equals 2, we get a quarter. The point is somewhere here. So then at the quarter, we get an open circle because 2 is not in the domain. So the rest of the graph is the same, except this open circle. So this keeps going. This keeps going in the third quadrant. Okay, so basically the two graphs are the same except at one point, except at a 2, quarter. So this point is on the first one, but it's not on the second one. So that's the difference. So this one we call removable singularity because it was supposed to be vertical asymptotes. However, because this is canceled, so it became a removable singularity. So the difference between those two functions, we could see the graphs are different, right? Because the second graph has a 1 point less, and the domain are different. The domain of f is x, is all real numbers, but not -2. Domain of the g is x can be all real numbers, but -2 and 2. Okay, that's B. Now let's see C. So C is similar, right? Let's just simplify the second one first. We see the denominator here, the denominator can be factored as x squared, oops, -4. Then in the numerator, we have x as a factor. In the denominator, we have x as a factor. So g, function g can be simplified to be f. Yeah. But the domain will be different. So x squared -4 can be factored as x plus 2 times x minus 2. So the domain of f is x not equal to -2 and 2, right? Not equal to, so let me slash this equal sign. But the domain of the second of g is x not equal to 0, -2 and 2. Right, because if x is 0, it will cause the denominator to be 0, right? Right? We have to look at the original function. So when we graph, so this graph will be a little bit difficult. So let's see, how do we graph f? First, we look at this 1 over x squared. So we know the reference graph of 1 over x squared, which is one piece in the first quadrant. Oh, sorry. I need to erase this. Let me see. Right, because I need to draw the vertical asymptote first. I want to draw x equals to -2 and x equals to 2. I only want to erase this one. Okay, good. So let's see, this is a 2. So I have vertical asymptotes at 2. So let's draw the vertical asymptotes first. X equals to 2 and x equals to -2. Those vertical asymptotes. So this is a -2 and this is 2. I have these two vertical asymptotes. So because the reference graph of 1 over x squared, so I have these two pieces. I have this piece. This is the same when x approaches -infinity, function value approaches 0. When x approaches to -2 from the left-hand side, function value approaches positive infinity. Then I have this piece. When x approaches to positive infinity, function value approaches 0. When x approaches to +2 from the right-hand side, function value approaches positive infinity. So that's n behavior. But then what about in between -2 and 2? In between of -2 and 2, let's see, let's find a y-intercept. Y-intercept means x equals 0, right? If x equals 0, we plug in 0 for 0 squared is 0, 0 minus 4 is -4. So we have -1/4. Somewhere here, let's see, this is -1/4. All right, so this is a 1, maybe this is a -2. Right, but my drawing won't be exact. Okay, so I have this point. Maybe we evaluate at a 1 and at a -1 also. So evaluate at a 1. If x equals 1, 1 squared is 1, 1 minus 4 is -3. So I get -1/3. So I get -1/3. is even smaller somewhere. Negative 1/3. So this is a negative 1/4, right? Negative 1/3. It's a little bit bigger than this. It's not exact. So negative quarter should be here. The negative 1/3 is a little bit, right? So negative 1 is the same. You see, negative 1 squared is also positive 1. 1 minus 4, that's minus 3. So also negative 1/3. Then we can evaluate more, but for this, I have enough. Because I know my graph won't go over the vertical asymptotes. So I know my graph will go this way. So usually 3 points are good enough, right? Because those are vertical asymptotes, so my graph has to behave this way. And because also it's an even function, so you see the graphs are symmetric with y-axis. So that's my graph for F. For second one, the difference, because that difference is in domain, because 0 is not in the domain. So the graph is supposed to be very similar, but differ in 1 point. So this is the asymptote, vertical asymptotes at x equals to -2. This is the vertical asymptotes at x equals to +2. And when x equals 0, supposedly from the first one, we should have -1/4. But for this one, x cannot be 0. So what happens? We have this open circle. Then the rest of the graphs are the same. So only we have this 1 point different, right? Then because 0 is not in the domain of the second one, so the rest are the same, right? So the graphs of those two, and the domain differ in 1 point, which is 0, and the graphs are differ in 1 point, which is also at 0. Okay, so that's this one. Let's see, 2. So we want to match rational functions with the graphs are given. So we're going to look for the obvious characteristics. So let's see the first one. The first one, we have the denominator. So we look for vertical asymptotes or horizontal asymptotes, right? So x cubed minus 27, if we remember, that can be factored, right? So x cubed minus 27 is x cubed minus 3 cubed. So that can be factored as x minus 3 times x squared plus 3x plus 3 squared, which is 9. So you see x equals 3 is a vertical asymptote. So let's just look for, which one has a vertical asymptote at 3, x equals 3. Oh, this one, you see D? Right, D has vertical asymptotes at x equals 3. And the degree of the numerator is 1, degree of the denominator is 3. So the horizontal asymptote is y equals 0, which is the x-axis. And that's it. So the first one should be, and then there's only one vertical asymptote. So something similar is this 4. 4 has a denominator of x squared minus 9, but it has 2 asymptotes, has 3 and -3, right? So it's not 4. So D is 1. So let's write down this for D. So the first one, let's write it. This is D. Okay. Now let's look at 2. 2, 3x. Let me bring the denominators. We focus on the denominator. We're looking for vertical asymptotes, right? So we can factor out 3. Once we factor out 3, we'll have x squared minus 4. So that can be factored as x plus 2, x minus 2. And then nothing can be simplified. So x plus 2, x minus 2 is not factored in the numerator. So cannot be simplified. So we're looking for 2 vertical asymptotes, which is at -2 and 2. So we look for the graph to see which one has vertical asymptotes at 2 and -2. Oh, F, right? You see F, vertical asymptotes at -2, vertical asymptotes at 2. Bingo, so F. Okay, let's write down F. Oops. F. Okay, now let's look at 3. 3, we also can factor. We can factor x. So once we factor x, we have x squared minus 16. X squared minus 16 can be factored as x minus 4 times x plus 4. Now we have 3 vertical asymptotes, right? Because the numerator doesn't have any common factor with the denominator. Nothing can be cancelled. So we have 3 vertical asymptotes at 0, x equals 0, which is the y-axis, and at 4 and -4. Now, so let's look for which graph has 3 vertical asymptotes. Oh, this one, E. You see at -4, at 0, at 4, right? So that's it. So 3 is E. It's E. Now let's look at 4. 4, we have x squared minus 9. This can be factored as x plus 3 and x minus 3. So we get 2 vertical asymptotes at 3 and -3. Because it cannot be simplified with numerator, right? So we have 2 vertical asymptotes, 3 and -3. Right here, C. You see, -3 vertical asymptotes at 3 vertical asymptotes, right? So 4 is C. So let's write down not E, C. Then let's look at 5. So let's see 5. 5, the denominator can be factored as x minus 4, x plus 2, right? So we have vertical asymptotes and cannot be simplified with the numerator. So we have 4 and -2 as vertical asymptotes. 4 and -2. 4 and -2. So B, right? So vertical asymptotes at -2 and the vertical asymptotes at +4. So it's B. B. Okay, last one, 6. 6 at -2, which is 8, right? And that's it, all right? So I think that finishes, right? That finishes. Yeah, that's the last question.